Welcome back, everyone. We are on lecture 6 of our Introduction to Glass Science course, and we are currently in chapter 3 of the textbook. So today's lecture is on the topological theory of glass formation. This is the second of 3 lectures that will be associated with chapter 3 of the book. Last time we introduced the structural theory of glass formation, and that was given in terms of Zachariason's rules for glass formation. Recall what Zachariason did was he considered some oxide potential glass forming compound, which is given by the general formula A sub M, O sub N. So the oxygen here is the anion, and A is representing some cation like silicon or boron or aluminum. And Zachariason had 4 rules of glass formation. The first 2 rules defined the short-range order. Rule 1 states that an oxygen atom is linked to no more than 2 atoms of the cation. So this is telling us how many cations are around each oxygen. And then the second rule tells us how many oxygens are around each cation. The second rule says the oxygen coordination around the cation A is small, say 3 or 4. So when you take these first 2 rules together for this oxide compound, what this is defining is that you've got 3 or 4 oxygens around each cation, and then this forms kind of a cation-centered polyhedron, which would either be a triangular shaped polyhedron or a tetrahedron. Triangle if it is 3 coordinated, and tetrahedron if it is 4 coordinated. And then the oxygen anions are at the corners of that polyhedron. The oxygen cations then serve as bridges to link these neighboring polyhedra together. And the last 2 rules tell us about how those polyhedra are connected together. So rule number 3 states that the cation polyhedra share corners, not edges, not faces. So if you've got triangles or tetrahedra, it's the corners of the triangles or tetrahedra that are sharing with each other through those bridging oxygens. And then the last rule states that at least 3 corners are shared. And the overall goal of these 4 rules that Zachariason postulated was how could you make a structure to give a disordered network in 3 dimensions? So how could you make something that has basically an infinitely large unit cell with no repeat units? And the way to do that is by having these basic structural units with short range order, but then connect them together in a way such that you have decreasing order as you get to the intermediate regime, and then a complete lack of long-range order. So Zachariason was thinking in terms of oxide systems, and this has had a huge impact on our thinking about glass structure. Today, what we're going to do is get into the second of our 3 most important theories of glass formation, and this is the topological approach. And this was originally due to Jim Phillips, who is a physicist who has had some major contributions to condensed matter physics pretty much every decade of his career, going back to the 1950s when he invented pseudopotential theory. This particular approach was published initially in 1979. He has published extensively on it since then, and a lot of other researchers have also contributed to this and extended the theory and provided a lot of experimental validation as well. So this topology here is referring to how the atoms are connected together. So it's slightly different than structure. Structure is kind of about the positioning of the atoms, and the topology is how the bonds form to create a network of atoms in this disordered glassy state. So we will be covering an introduction to this theory today. And then next time in the next lecture, we are covering the kinetic theory of glass formation, which is the most general theory of glass formation. Jim Phillips originally proposed his topological constraint theory in the context of covalently bonded chalcogenide glasses or chalcogenide glasses. But even though this theory was originally proposed in the context of chalcogenide glasses, it is applicable to any type of glass chemistry, just like how, Zachariason's theory was proposed in the context of oxide systems, we can also apply it to non-oxide systems as well. Now, Phillips's topological constraint theory was based on counting the number of rigid bond constraints in the glass network and comparing that number of rigid bond constraints to the number of atomic degrees of freedom. The basic principle here is that if you think of each atom as like having some position in a three-dimensional space, in order to define that position in three-dimensional space, we need to give it three coordinates. We need to give it an x position, a y position, and a z position. Now, every time you add some sort of rigid bond to the network, whether it is a rigid kind of pairwise bond, a radial bond, or a rigid bond angle, what you're doing is actually taking away one of those degrees of freedom because the atoms can no longer move about freely in space anymore because they are constrained to be at a certain position or a certain angle relative to the other atoms. So every time one of these constraints is added to the system, it removes one of the degrees of freedom. And the basic postulate of Phillips's constraint theory is that optimized glass formation occurs where the number of these bond constraints equals the number of degrees of freedom. And we'll walk through in this lecture what exactly do we mean by that? How do we calculate the number of constraints and the number of degrees of freedom? And how do we determine what the optimized glass forming chemistries will be? So that's the goal for today. This approach was actually inspired by civil engineering and architecture. If you look at most bridges and many buildings, such as the Eiffel Tower shown here, you'll note that this is not composed of squares or other types of quadrilaterals. Rather, these buildings are composed of triangles. And the reason that they are composed of triangles is that the triangle is a perfectly rigid object when used in architecture. Basically, if you've got three bonds that are connecting each of the three vertices of the triangle, it's not possible to deform that triangle and change the angles because the rigid bond distances there along all of the three edges of the triangle are preventing you from changing the angles. On the other hand, if you were to try to build, say, the Eiffel Tower out of squares instead, with a square, you could continuously deform the angle without changing the distances between the vertices. And so you don't have that same degree of rigidity with a square as you would with a triangle. And this is one of the basic principles of civil engineering to ensure that you've got an optimally rigid structure. And what Phillips did was to take those same principles and instead of applying them to these, large buildings or bridges, actually apply it at the atomic scale to the atomic structure of glasses, and then use that to determine what type of glass chemistry would give you the optimum structure. Now, as I mentioned, Phillips was working in the context of chalcogenide glasses. And if we look at the periodic table, the chalcogen column of the periodic table is this number 6 group here that starts off with oxygen. Most of the time in glass science, we are dealing with oxide glasses, and that's where oxygen is the anion. And in Zachariason's structural view of glasses, he was considering specifically oxide glasses. But if you go downward, so down from oxygen to these lower rows in the periodic table, the next one is sulfur, and then selenium, and then tellurium. And when we say chalcogenide glasses, what we generally imply is that it involves at least one of these chalcogen elements. So it also is implied that it is a non-oxide glass. And so this would mean it's either a sulfide glass, a selenide glass, or a telluride glass, or some combination of those three chalcogen elements. And the other elements that are often added to chalcogenide glasses are, if we go over to the left here, arsenic or antimony here in group 5, and then often germanium is another element that is used here in group 4. Now, for these covalently bonded glasses, chalcogenide glasses, you can continuously vary the ratios of all of these elements with each other. So you don't have to satisfy any specific type of stoichiometry in terms of like how much germanium there is relative to selenium. You can continuously vary that chemistry and in principle make glasses out of that. And part of the goal of Phillips's theory is to predict then what the optimum ratios would be based on having this kind of optimally rigid glass network. And in case you're wondering, what are these chalcogenide glasses used for? If you remember back to our second lecture on glass compositional families, chalcogenide glasses are known for their good optical properties in the infrared. So basically, if you start off with an oxide glasses are very good, usually for having transparency in the visible. Then if you go to larger and larger atoms, then that low loss transparency window is being shifted to longer and longer wavelengths, or in other words, lower energies. And so when you go from an oxide glass to a sulfide glass, that gives you greater transmission in the near infrared. As you go to selenide and telluride glasses, it pushes the transmission window further into the mid-infrared. So these chalcogenide glasses are mostly used for infrared optical applications, and so that's why we care about this from a technological point of view. Now, like oxygen here, these group 6 elements, sulfur, selenium, and tellurium, in order to satisfy their outer shell of the electrons, they need to be 2 coordinated. And so this M here is indicating the coordination number of those particular elements in this column. The coordination number for these group 6 elements is equal to 2. So it's just 8 minus the group. So 8 minus 6 is 2. If you go to the left here for these group 5 elements, the coordination number is 8 minus 5, which is equal to 3. So arsenic and antimony prefer to be threefold coordinated. And then for the group 4 element here, for germanium, just like silicon, you've got 8 minus 4, that equals 4. And so the coordination number of germanium is preferred to be 4. Now, the key parameter in Phillips's topological constraint theory is the average coordination number of the potential glass forming system. The average coordination number here is indicated using these angle brackets as the average around the coordination numbers. And if we write this out, what this means is that if you take the summation over all the species in the glass, so all of these species I, and if you've got a mole fraction of each of those species, x sub I, multiply that mole fraction by the coordination number of that species, m sub I, and this gives you then a weighted average of the coordination where the weighting is done by the mole fraction here, xi. So taking these coordination numbers, 2 for sulfur, selenium, and tellurium, you would use the mole fractions of sulfur, selenium, and tellurium. That gives you its contribution to the average. Then you'd have the coordination number of 3 using the mole fraction of arsenic and antimony, and then the coordination number of 4 using the mole fraction of germanium. And then that weighted average gives you the average coordination number, this M in angle brackets. Now, the next step is how do we go from the coordination number to actually counting the constraints? Now, Jim Phillips was working in the context of these covalently bonded chalcogenide glasses, and in covalently bonded systems, the general assumption is that you've got both rigid bond distances, meaning the distance here between these two bonded yellow atoms is a fixed quantity. This is what's called the two-body constraints or the radial constraints based on having a rigid bond distance. And then there is a second term here, which is the three-body constraints or the angular constraints. because with covalently bonded systems, you have not just rigid bond distances, but there's also strongly preferred bond angles. And so those rigid bond angles provide an additional rigid constraint in the system. So what we need to do here in order to sum up the total number of constraints here, this capital M sub C, is that we need to sum up over all of the two-body radial constraints and all of the three-body angular constraints in the system. And what we have here on the right-hand side of this equation is we're just summing up over all the mole fraction of each of these species over all the different species here, I. And then for each one of those species, based on its coordination number, M sub I, we can get the total number of two-body constraints and the total number of three-body constraints. So let's start with the two-body constraints. The formula here for the two-body constraints is just the coordination number divided by 2. So this coordination number is telling us how many nearest neighbors that the atom has. So if you've got a coordination number of 2, like these yellow atoms, you see that there are 2 bonds connecting them. If it's a coordination number of 3, may have 3 bonds, like these purple atoms, or a coordination number of 4, like these turquoise atoms here, having 4 nearest neighbors. So why is there a division by 2? The division by 2 is there because each bond is shared between 2 atoms. So if we consider this yellow atom here on the left, this yellow atom is bonded to 2 other atoms, but each one of those bonds is shared between those 2 atoms. And so on average, it's just 1 full bond per atom. Or in other words, we take the total coordination number here and divide by 2 because each one of those bonds is being shared by 2 atoms. And so in order to avoid overcounting the constraints, we need to take into account that sharing. So the coordination number divided by 2 gives us the total number of two-body constraints. So if we have a 2-coordinated atom, that means it's 2 divided by 2, or 1 bond per atom. If it is a 3-coordinated atom, then you've got 3 divided by 2, which is 1.5 rigid constraints per atom. And if it is a 4-coordinated element like germanium, then you'd have 4 divided by 2. So in other words, that is 2 rigid radial constraints per atom. So that is this first term. The second term is summing up over all the angular constraints in the system. And in order to understand this, let's start off with a coordination number of 2. So if you consider the yellow atoms here, and just look at this figure, how many rigid angles are there? And you can very easily see that there's just 1 rigid bond angle here for a 2-coordinated system. It is this subtended angle here going among these 3 atoms here. So this angle shown by my pointer here, that is the rigid angle, the 1 rigid angle for this 2-coordinated system. So if you take the coordination number of 2, and it's 2 times 2 minus 3, so 4 minus 3 equals 1. This is telling us that we have 1 rigid bond angle for a 2-coordinated system. And that is exactly right. So for this 2-coordinated atom here, you'd have 1 2-body constraint and 1 3-body constraint. So the total number of constraints would be 2. Now, if we go to a 3-coordinated element here, like arsenic or antimony, and if we put in the number 3 here, you've got 2 times 3, which is 6, minus 3 is 3. And that is because there are 3 angles, 3 bond angles that need to be defined for a 3-coordinated system. So you'd have 1, 2, and then 3 going across. So if you consider, say, this lower purple atom is bonded to 1, 2, 3 atoms. There is 1 angle here, there's another angle here, and then there's another 3rd angle. So if you look at every pairwise combination of atoms and you add them up, then there are 3 of them. Now, the other way to think about this, and actually kind of the better way to think about counting the angles, is that every time that you add an additional neighbor, an additional coordinated neighbor to an atom. So if we suppose you've got this purple atom here, and it's bonded to two atoms. And now we're going to add a third atom here, this third purple atom. How many additional constraints do you need to fully define the position of that third atom? And if you've got this as an additional coordinated neighbor, that means you've got one bond that is defining one of the coordinates of the system. And so that one bond is going to take away one of those degrees of freedom. Now, if this is existing in three-dimensional space, how many coordinates do we need to define the position? We need three coordinates. We need to know the x position, the y position, and the z position. And if you define a bond distance, basically that's taking away one of those coordinates that need to be defined. That means we need to define two additional coordinates in order to pin down the exact location of that atom. And so if there's one radial bond, then that means we need two angular constraints in order to pin that down. And that is the fundamental reason why there is a multiplication by two here. So every time we increase the coordination number by one, we need to define not just one additional bond distance, but two additional bond angles as well. So that's why we have 2 times the coordination, and then the -3 is just to get the right number of angles. If you start off with a coordination of 2, you should end up with 1 angle that's necessary. If you go to the coordination of 3, you'd have 3 bond angles, and every time you increase the coordination number by 1, that increases the number of angles by 2. So we go from 1 angle to 3 angles, and then to 5 angles for the 4 coordinated system. You'd have 7 angles. So five angles for the 4 coordinated system, 7 angles for the 5 coordinated system, and so on. So if you put in a 4-fold coordinated atom here, 2 times 4 is 8, -3 is 5. So there would be 5 angles in this case that need to be defined. Now, putting this all together, this would give us the total number of constraints in the system by adding up all of these 2-body constraints in this first term and adding up all of the 3-body constraints on the second term. And what Phillips did was he postulated that the optimum glass formation is going to occur where the number of rigid constraints is exactly equal to the number of degrees of freedom in the system. And so what he proposed is that the best glass formation would occur where this number of constraints here on the left is equal to the number of degrees of freedom on the right. What is defining the number of degrees of freedom? The number of degrees of freedom is just the number of different ways that you can position the n atoms in the system. So if you've got a total of n atoms in the system, each one of those n atoms has 3 positions that need to be defined. It's x, y, and z position. So the total number of degrees of freedom is 3 times n, 3 times the number of atoms. And if we write this on a per atom basis, that's this third line here, the right-hand side is just 3 degrees of freedom per atom. Now, the left-hand side of the equation here gives the total number of constraints, which is set equal to the number of degrees of freedom, according to Phillips. From the previous slide, we have our total number of constraints as summing up over all of the 2-body and the 3-body constraints. If instead of writing this out for each individual atom, we do an average of all of the atoms using the average coordination number, which is this little m in angle brackets, this would be the average coordination number per atom of the system. So the total number of radio constraints, or the average number of radio constraints, I should say, is the average coordination number divided by 2. And then the average number of angular constraints is 2 times this average m minus 3. So you've got a summation of the radio constraints plus the angular constraints. And when there is optimized glass formation, this left-hand side of the equation, the average number of constraints should be equal to the number of degrees of freedom per atom. So in other words, we set this left-hand side of the equation equal to 3 translational degrees of freedom per atom. And then the next step is to solve for m. We solve for this average M, and this gives us the optimum value of the average coordination number of the system to satisfy this condition of the number of constraints being equal to the number of degrees of freedom. So solving for this M, what we get is M is equal to 2.4. And in other words, the optimized glass formation, according to Phillips, occurs where the average coordination number of the system is equal to 2.4. And this value of 2.4 is given a special name. It is called the rigidity percolation threshold, M sub P. It is called the rigidity percolation threshold because this is where the entire glass network would become rigid. Or in other words, there's enough rigid radial bonds and enough rigid bond angles such that there are no further degrees of freedom in the system, because the way that we derived this was by setting the number of constraints equal to the number of degrees of freedom. The way to achieve that condition is by having the average coordination number equal to 2.4, which is defined to be this rigidity percolation threshold. So according to Phillips, if your glass network is designed such that the average coordination number is equal to the rigidity percolation threshold of 2.4, then the optimum glass formation would occur. Now, what are some of the implications of this? What happens if you have an average coordination number that is less than 2.4? If your average coordination number is less than the rigidity percolation threshold, then the network is called under-constrained, meaning that the number of constraints you have is fewer than the number of degrees of freedom. This means that you don't have enough bonds in the system to really pin down the exact locations of all of these atoms. And what that means is that you're able to deform the atomic structure of the glass by moving the atoms around because there's not enough bonds there to keep them in place. Um, this is also called a floppy network. Floppy because atoms would have the ability to rearrange themselves with a very low cost in energy because there's not enough bonds to hold them in place. And if you have an under-constrained system, then these atoms could easily rearrange themselves in order to find a minimum in the free energy of the system. In other words, it would be very easy for them to move around and crystallize. So an under-constrained system is not an ideal glass former because it's too easy for the atoms to move around and crystallize. So glass formation is not optimal here for an under-constrained system. Likewise, if you go to an over-constrained system, an over-constrained system is where the average coordination number is greater than the rigidity percolation threshold. So the average coordination number is greater than 2.4. In this case, the system is called over-constrained because the number of bonds is too many. You have too many bonds that are putting too much rigidity in the network, more rigidity than you have degrees of freedom. Now, if you have a disordered structure, a disordered glassy structure, and you try to apply too many bond constraints on the system, those bond constraints tend to be mutually incompatible because of the disordered structure. And what this means is that you've got, say, a bond distance between two atoms that wants to be a certain length, and then other bond distances that want to be certain lengths, or bond angles that want to be at certain angles, but the system is unable to satisfy all of those constraints simultaneously because of the disorder in the glassy structure. Now, this kind of incompatibility of these constraints means that there's local stresses in the glass network. Those local stresses provide a driving force for the network to crystallize, because the way to satisfy all of these bond constraints simultaneously is to get rid of the disorder in the glassy state. So if you've got an over-constrained system, there is a large thermodynamic driving force to eliminate the stresses that are being caused by having an over-constrained system. And the way to relieve those stresses is to impose crystalline order on the system. So an over-constrained system will also be quite easy to crystallize because of this large driving force to get rid of the stress in the network. So an under-constrained system is non-optimal. An over-constrained system is also non-optimal. The best glass formation, according to Phillips, is where the average coordination number is exactly equal to the rigidity percolation threshold of 2.4. And in mechanics or in civil engineering, this is what's called an isostatic system. This is where you've got exactly the right number of constraints to fully define the coordinates of the system. So you've got just the right number of rigid bond distances and rigid bond angles to pin down the locations of each of the atoms. And one of the byproducts of this is not only would you have optimum glass formation at the rigidity percolation threshold of 2.4, but we might also observe certain critical behavior or extrema in properties of glasses around this average coordination number of 2.4. So let's consider a sample chalcogenide glass system here. One of the most studied chalcogenide glass systems is the germanium-selenium system. So this just has germanium in it, which is 4 coordinated, and selenium, which is 2 coordinated. And you'll note that the structure is actually kind of analogous to the silica structure, right? So silicon, like germanium, is 4 coordinated, and selenium, like oxygen, is 2 coordinated. So the basic structural unit here is a germanium centered tetrahedron, just like the basic structural unit in silica is the silica tetrahedron. And connecting the tetrahedra here in this system is selenium, whereas in silica, the connection is provided by the bridging oxygens. So what are the constraints here in this germanium-selenium system? When we consider the germanium here, you see that there are 4 bonds because the germanium is 4 full coordinated. The selenium has 2 bonds, and each one of these bonds is shared between 2 atoms. So in terms of the radio constraints, there would be 2 divided by 2 radio constraints for each selenium. So you've got 1 radio constraint for each selenium. For germanium, you've got 4 bonds, each shared by 2 atoms, so it's 4 divided by 2, or 2 rigid constraints, radio constraints for the germanium. So 1 for each selenium and 4 for each germanium in terms of the radio constraints. For the angular constraints, if we just jump down here for selenium, this is a 2 coordinated atom, and so you just have 1 rigid bond angle. When we go up to germanium, we add 2 angles for each increase in the coordination number. So we're going from a 2 coordinated selenium up to a 4 coordinated germanium. So we go from 1 angular constraint to 3 and then to 5. So there are 5 angular constraints here around the germanium. There's 4 inside the tetrahedron, and then 1 additional bond angle that needs to be defined in order to pin down all of the atomic positions in this tetrahedron. So 5 angular constraints per germanium, 1 angular constraint per selenium. And if you add up all of these, that would give you the total number of constraints in the system. Now, how do we find the best glass forming system in this germanium-selenium system? What we need to do is calculate the average coordination number as a function of composition. So if we consider a chemical formula here of GeX Se1 minus X, so X is the mole fraction of germanium and 1 minus X is the mole fraction of selenium. And if you add these up, you get a total of 1. So, so that means that we are properly normalized here. So X plus 1 minus X will give us 1. Now, the average coordination number of the system would be, we need to sum up over both species. So this first one here, 4X, this is the contribution from the germanium. We've got X mole fraction of germanium, and the germanium is 4 full coordinated. So this contribution here is 4X. With selenium, the mole fraction of selenium is 1 minus X, and the coordination of selenium is 2. So we've got plus 2 times 1 minus x. So this first term is the contribution from the germanium. The second term is the contribution from selenium. And in order to get the optimized glass former, we set this average coordination number on the left equal to the rigidity percolation threshold of 2.4. So we set this equal to 2.4, and if we solve for x, this gives us the optimized glass former occurs at x equals 0.2. So in other words, this occurs at GE 0.2, SE 0.8. This is how you would write it in terms of mole fractions. Or if you were to just multiply both of these subscripts here by 5, another way that you could write this is as GeSe4. And so according to this prediction, in this binary system of germanium selenium, the optimized glass former of this binary germanium selenium system occurs at an x equals 0.2 or at GeSe4. And if you take this x and you plug it back into the equation, you can readily see how this comes out. So if you put the x equals 2 here, you've got 4 times 0.2 plus 2 times 0.8, which equals 2.4. And how does this agree with experiments? If you look at, this is kind of a qualitative mapping of the glass forming difficulty in the germanium selenium system as a function of the atomic percent of germanium here. And what we see is that the difficulty of forming a glass, meaning basically how easy does the system crystallize, this goes through a minimum at this germanium concentration of 20%, 20 atomic percent. This is a minimum in the ability of the system to crystallize, which means that it is a minimum in the glass forming difficulty. And if the difficulty is at a minimum, this means this is the best glass former. So the best glass former here occurs where this curve is at a minimum, and that occurs at 20 atomic percent of germanium, which is exactly equal to our x equals 0.2. So this is just showing how Phillips's topological approach actually gives us a very accurate prediction of what the optimum glass formation would be. Now, these glasses have some very interesting behavior as well. I'm going to show you some, actually some atomic scale simulations that I did back during my PhD research a while ago. So this shows a nano indentation simulation of kind of a slice of germanium selenium glasses. So this is GeSe4. This is the isostatic glass. Isostatic because this is where the average coordination number is equal to the rigidity percolation threshold of 2.4. And if we start off with our initial glass here, this dashed line is showing the initial surface of the glass, and we bring down this invisible indenter, you can see that the atoms here are going to either they need to get out of the way of the indenter as it's brought down. You can see the indentation coming down more, and more and more. So as we go, starting at the top to the right and then across the bottom row, we are increasing time here as the indenter is being pressed into the glass. And there are two basic ways that the glass can accommodate the indentation. You can either have densification of the atoms underneath the indenter, or the atoms can flow out of the way and rise above this initial surface. So going above this dashed line, and you can see that we actually have quite a bit of that occurring in this GeSe4 system because you've got this kind of cooperative flow of the atoms to get outside of the range of the indentation. And what happens is that they form this pileup around the surface. And in fact, if we look at, if we just kind of count the number of atoms that fall above the original surface, so count all the atoms falling above this dashed line, as a function of average coordination number, so changing the composition of the glass to get all these different coordination numbers, the mound size at the maximum load of the indenter goes through a maximum at the average coordination number of 2.4. So this is what I meant when I mentioned earlier about extremum behavior in glass properties as a function of average coordination number and seeing maxima or minima around the average coordination number of 2.4, because this is the optimized glass network, and this is actually giving us a maximum of the cooperative shear flow, leading to these mounds around the indentation. If you take a look at what's happening here in, say, an overconstrained system, this is a GESE system. What's the average coordination number here? This is very easy to calculate. The germanium has a coordination of 4. The selenium has a coordination number of 2. They're occurring in identical concentrations, so the average coordination number is just 3. So that's this point down here where the mound size is a minimum. What's happening here after the indentation is that these green arrows are showing you how much the atoms are moving in response to the indentation. And what's mostly happening here is that the atoms are taking the minimal amount of movement possible just to get out of the way of the indenter. That's leading to some permanent densification of the glass, and the atoms aren't really able to flow that much because of having so many additional bond constraints. If you go to the opposite side here, so this is a GESE17 system, this is where you've got way too much selenium, so this is an under-constrained glass as opposed to an over-constrained glass. Because it's under-constrained, the atoms don't have enough rigid bond constraints, so they can move around very easily. And what you see by these very long green arrows here are that the atoms are able to move a lot more in this under-constrained system. But there's a lot of disorder to this movement because the atoms are allowed to move, or many of them, largely independently of other parts of the glass network. And so you get a lot of this kind of random motion. However, if you look at GESE4, the isostatic glass, this optimized glass, what you'll see is that you've got medium length arrows as expected in between the two, but there's really good alignment in the direction of these arrows. There's good alignment because of the isostatic nature of the system here, which means that the atoms can flow, but only cooperatively with each other. So there has to be cooperative motion, and that cooperativity is what's giving you the alignment of these arrows and ultimately leading to this maximum in the mound size. You can also see this in terms of the elastic recovery of germanium selenium glasses. In this case, instead of having a spherical indenter, this is just kind of doing a flat press, doing kind of a uniaxial compression onto the glass and then releasing that and then seeing how much elastic recovery we have. So this is GESE glass. This is our over-constrained glass. Before it's put under uniaxial compression. This is under the maximum loading of the compression, so you can see how it compressed as a result of that uniaxial load. And then after releasing the stress on the system, the question is how much of the initial strain here, how much of those initial dimensions are recovered after releasing the stress. And if you had full elastic recovery, this would completely bounce back to this dashed line where the initial surface is. But what you can see is that in this over-constrained system, this GESE system, only part of the initial dimensions are recovered. There is some permanent plasticity that is a result of the atoms being over-constrained here. For the isostatic system, the GESE4 system, this actually gives perfect elastic recovery under these conditions. And this is again showing that the structure of this glass is the most resilient to distortion because of its isostatic nature. So here, if you look at the surface before loading and then under loading, and then when you remove the load, the initial dimensions get recovered. So there's 100% elasticity in that case. Now, one last topic here on topological constraint theory is, as I mentioned earlier, there has been a lot of additional research on topological constraint theory in glass science that has been done in the decades since Jim Phillips wrote his initial paper in 1979. One of the researchers who has done who's been kind of the most prolific in this area is Professor Puneet Bulchand at University of Cincinnati, and he has discovered what's called the intermediate phase, and what other people call the Bulchand intermediate phase in his honor for discovering this. And this discovery was that there's not just kind of one point of transition between a floppy or under constrained system and a rigid or over constrained system, but for some systems at least, this single point can actually be split into two transitions. So it's no longer just a single rigidity percolation threshold, but two transitions. There is first a rigidity transition, which goes between a floppy network and what's called this intermediate phase or Bulchand intermediate phase. So this rigidity transition occurs here at the left. And then there is a second transition, which is called the stress transition. And the second transition occurs between the intermediate phase and this what's called a stressed rigid network. The idea here is that rather than having a single glass chemistry that is the optimal isostatic composition, that if there is enough ability within the glass network to kind of rearrange some of its local structure to relieve stresses, that there may actually be some finite width to this, such that the perfect isostatic glass networks can be obtained not just at exactly the rigidity percolation threshold, but over some range, over some width here. And if that is the case for a given family of glasses, then you can have optimized glass formation, not just a single composition, but over a range of compositions. And it's not until you get past this stress transition that the number of rigid bond constraints becomes so large that the structure can no longer accommodate it. And so the stress transition indicates the crossover from having an isostatic stress-free glass network in the intermediate phase to then having so many constraints that the system simply cannot relieve the stress. And when you start to get that buildup of stress, that's where you have the stress-rigid network. So here, the transition from the floppy network to the intermediate phase at this rigidity transition, this occurs when you go from an under-constrained system to an isostatic system. And then the second transition occurs when the system can no longer stay perfectly isostatic, but you've got stresses that start to build up. Now, Bulchand has mapped this out in terms of the kind of relaxation behavior of the glass, showing that in this intermediate phase window here, that there is a minimum in the what's called the non-reversing heat flow, which is a measure of how much the glass is able to age or relax. And he's shown as a signature of this intermediate phase that it goes through this fairly well-defined minimum in this non-reversing heat flow in calorimetry experiments. And based on these measurements, he's mapped out these reversibility windows for a wide variety of different glass chemistries shown here on the right. And these red lines are showing the measured bounds of the Bulchand intermediate phase that correspond to this reversibility window from the calorimetry experiments. So you can see here, let's say for the germanium-selenium system, that is given by this red line shown here, that the rigidity percolation threshold, the rigidity transition here is occurring at the average coordination number of 2.4, as initially predicted by Phillips. But what he's showing is that the structure can kind of accommodate a higher average coordination number up to about 2.52 before stresses start to get incorporated into the glass network. And in all of these cases, you can see that this reversibility window is not necessarily exactly centered around the average coordination number of 2.4, but it's pretty close to it. So I think it's helpful to think of the initial work by Phillips giving the rigidity percolation threshold of 2.4 as kind of a simplified or kind of the most simple version of topological constraint theory, but there may be additional complexities such as this intermediate phase work by Bulchan. And I should also point out that this is still very much an active area of research with a lot of debate going back and forth between different groups about what these results mean in terms of the properties and the structure of the glass. So if you want to learn more, please let me know and I'd be happy to send you additional papers. All right, so to summarize the topological constraint theory of glass formation, the optimized glass formation occurs where the number of bond constraints is equal to the number of atomic degrees of freedom. For a covalent system where we have both rigid bond distances and rigid bond angles, this occurs with an average coordination number of 2.4. And using that, then we can then calculate what those chemistries would be that satisfy the average coordination number of 2.4 and therefore give us the optimized glass formation. However, more recent work has extended the theory, such as the work of Bulchan, showing two thresholds, a rigidity transition and a stress transition, which leads to this intermediate phase. All right, so next lecture will be the kinetic theory of glass formation. This will be the most general theory of glass formation. I will see you then. Thanks, everyone.